Hello everyone. I'm going to do the day 6 and day 7 notes. I'm going to go relatively fast through these. You can kind of pause and look at the work as you need to, but I want to make sure that I get through this sooner rather than later. So we'll start with projectile motion, and one of the things we want to say in day 6, the x direction velocity is going to be constant because there is no acceleration in the x direction. What happens in projectile motion? There will be only one force present, and that force is gravity, and gravity pulls things down. So there is no x direction force, therefore no x direction acceleration, and we see that acceleration is y direction only caused by gravity. That will be negative 9.81. Also, the symmetry of the y direction for velocity, if we see this trajectory in blue and we are focusing only on y direction velocity, there is x direction velocity as well, but for the moment only on y direction velocity, we see that the velocity vectors point up as the projectile goes up, 0 at the peak, and then the vectors point down. One of the key things we'll note though is magnitude-wise, if two points are at the same elevation, such as A and G, B and F, C and E, the magnitudes of those velocities are equal to each other. So the biggest trick to solving any of the projectile motion questions is to make sure that you keep information about the x direction and the y direction separate from each other. The only thing they can share in common is time. So we'll start with this problem here. We have Mittens, the destroyer of worlds, as we see, is chasing you. You are running at 8 meters per second. You jump off this cliff. When you jump off the cliff, it is 12 meters tall. So let's start by figuring out what information we have. For velocities, we have a v initial of 8. It is x direction only. You are running horizontally. The v initial for the y is 0. Then we have accelerations. Acceleration for x is 0. There is no force right or left. The only force present once you leave the cliff is gravity, and that is 9.81 meters per second squared down. We also see a change in height of negative 12 meters. My number one piece of advice on any of these problems is if you don't know where to start, try to find time. So try to find time. I have very limited information in the x direction. I'll get back to the x direction in a moment. So I'm going to go to the y direction to find time. To find time, the second equation is going to help me. What's nice is the v initial t component of that equation will cancel out because there is no v initial in the y direction. The 8 is purely x direction. From here, plug in numbers, and now we turn to a calculator. This will be the square root of 12 divided by 4.905. If I can access my calculator. And I got a time of 1.56 seconds. So 1.56 seconds is t. I haven't actually solved any of the questions that they've asked me. I've just figured out that time is 1.56 seconds. Now, that's very valuable because time can cross the physical dimensions x and y. So, I now have a new piece of information for the x direction, even though I solved time using y direction values. Now, what's going to happen with the x direction is your three equations, there's only one that ever works for the x. The first equation, because the acceleration is 0, tells you nothing more than the initial velocity and final velocities are the same. The third equation does the exact same thing. So the only thing that happens is the second equation has a 1/2 at squared canceled out, and it leaves you with delta x is v naught t. This is all that's ever going to be useful for the x direction because your acceleration is 0. And so we'll solve delta x. Delta x is 8 times 1.56. Therefore, 1.56 by 8 in the calculator gives me 12.5 meters. That solves question A, which asks for D, the distance shown here. The next thing I need is the final velocity. So that's going to be a composition of the x direction final velocity, which is 8, because velocity in the x direction is constant, as well as a composition of the y direction final velocity, which we can solve using the first formula. A quick run with the calculator, 9.81 by 1.56 is going to give me a velocity of 15.3, negative 15.3. So what we're going to do is build a triangle. The triangle is going to have a horizontal component of 8 and a vertical component of 15.3. I drew the vertical component down because it was negative, and the horizontal component to the right because it was positive. The resultant vector, what is your actual speed that you strike the water, is solved using Pythagorean's theorem, which hopefully you should be familiar with. So we have the square root of 8 squared plus 15.3 squared. The result is 17.3 meters per second. Now, that's only half of the information we need for velocity. We also need the angle, because velocity has direction. I'm going to use the tangent. So inverse tan of 15.3 over 8. You should be in degree mode. For physics, you will always use degree mode. I got 62.4 degrees. So that's 62.4 degrees below the x-axis, specifically the positive x-axis. And now I've answered the 2 questions. Again, you can pause, back up, and look again. I'm going to jump on to the next question to kind of try and speed things up. In this particular one, you are attempting to jump a lava pit. And the lava pit is 12 meters long. You are starting on a cliff that you will leave horizontally. You need to travel those 12 meters before you fall more than 5 meters. So we'll say delta x is 12. The goal of this particular problem is to figure out what is the minimum velocity required for you to make this so, well, you survive. Again, acceleration of the x does not exist. Acceleration for the y be negative 9.81 meters per second squared. The initial for the y is once again 0. This is a horizontal problem. So, when in doubt, find time. So that's exactly what I'm going to do here. More often than not, this equation is going to help you find time using the y direction in the second formula. It's not always going to be true, but I would say a good 80% of the time this is where you end up going. All right. A quick calculation gives me 1.01 seconds. 0.01 seconds for the time. And now I can take that and apply it to the x direction. Time gets to cross into the x dimension. As I discussed before, the only thing in the x that works is delta x is v naught t. And so that's exactly what I'm going to do here. 12 is v naught times 1.01. So we solve v naught, 12 over 1.01 gives me 11.9 meters per second. So that handles day 6. I'm going to go to day 7 now. Day 7 deals with flat ground problems and projectile motion. For flat ground, think of like a punted football where there's no change in elevation between where the ball starts and ends because you are on, well, a flat surface. A few rules, just like in the Rocket Lab. Your time up equals your time down. Your y component velocities are decreasing at first, but they are positive because the ball is going up. Then you reach the peak. At the peak, the velocity is 0 for y direction only. Then the velocities for y direction become negative, and they are increasing in magnitude. X direction velocities are constant. Your change in height is 0 because if you punt the ball, you started on the ground and you end on the ground. And the last one is what we call mirror angles. 45 degrees is the maximal range that can be achieved in a projectile under the influence of no air resistance. Now, 45 degrees plus or minus x degrees. So, for example, 30 degrees and 60 degrees are both 15 degrees away from 45. So 30 degrees and 60 degree projectiles will actually have the exact same range, but the 60 degree projectile will have a longer hang time because it has a higher upward initial velocity. As how do vectors look for projectiles? In blue is the y component of the velocities, and in green is the x component. The y component, as we can see over time, as the projectile moves, becomes smaller and smaller. The resultant velocity is a combination of the x and y's, as shown here in red. When we reach the peak, the resultant velocity is x only. So velocity total at the top is vx, because there is no y velocity at the peak. Then on the way down, the y velocity vector begins to increase in magnitude. And in red, once again, we see the result. The green vector for x does not change. Acceleration is always down, 9.81 meters per second squared. Accelerations are created by forces, and the only force present is gravity. So we have one example. In this example, a ball is kicked at a 30-degree angle above the horizontal. So in order to solve this, because x and y information must be kept separate from each other, we're going to use SOHCAHTOA to break up this triangle. So my v initial for the y is 25 sine 30, which is 12.5 meters per second. And my v initial for the x is 25 cosine 30. So v initial x would be 21.7 meters per second. We will once again make a chart just like we did before, separating x and y. Information that I know: acceleration is 0 for the x, and acceleration is negative 9.81 meters per second squared for the y. V initial for the x is 21.7 meters per second. V initial for the y is positive 12.5 meters per second. Due to symmetry, the final velocity for the y is negative 12.5 meters per second. Delta y is also 0 because we start and stop on the ground. So we have a lot of information about the y direction. The only thing we actually don't know about the y direction is time. And, well, strangely enough, question B asks, how long is the ball in the air? I can't actually answer question A unless I answer question B. So I'm going to start with question B. I can use either the first or second formula. It doesn't matter. I'm going to use the first one because I find it easier. Negative 12.5, and that negative is very important, is 12.5 plus negative 9.81 t. Okay, so that slide isn't working. There we go. The time that this ball is in the air will end up being 25 over 9.1, or 2.55 seconds. So 2.55 seconds. I can move that to the x column, 2.55 seconds. And now I've actually answered B. How long is the ball in the air? Let's backtrack and we'll answer A. Once again, x direction, delta x is v naught t. That's the only thing that's going to be viable because there is no acceleration in the x. 21.7 times 2.55 gives me 55.3. So 55.3 meters. That answers question A. The maximum height. Now, height is its separate own unique thing. And so let's not worry about what we have in the other charts. We're just going to do our own thing for height. One of the things that we will mention about height is it is controlled purely by the vertical elements. So gravity is present and our V initial of 12.5 is also present. I'm going to say V final is 0 because it's at the peak. Now, a huge, huge point that comes up in physics, what is the velocity of a projectile at the top? A lot of times people want to say it's 0. You are partially correct. The y component is 0. The x component is not. So the velocity at the peak is whatever the x component is. Now you'll see that I have used 0 for this because I'm only using information regarding the y. Now I have 7.96 meters for my height after running through the algebra and calculations. So that answers question C. Question D, the final question, is actually a lot easier than what it was on the last example that we had. And the reason being is because of the symmetry of the flat ground. The answer to D is it's 25 meters per second at 30 degrees below positive x axes. The symmetry, it was 25 meters per second above the positive x axis when it took off. Therefore, when it lands, 25 meters per second at 30 degrees below the positive x axis. Hope you enjoyed it.